Hello and welcome to this video about diagonalizing matrices. In the first step, we learned how to write a computer program to find the characteristic polynomial of a matrix. Now we're going to learn how to program a computer to find the eigenvalues of this matrix from this polynomial that we've just found. But first, here is a bit of theory. Supposing that V is the eigenvector corresponding to the eigenvalue called lambda, then multiplying this vector by its eigenvalue is equal to multiplying it by its matrix. Then we could manipulate this equation to look like this, so that the right-hand side is 0. Then we would factorize it like this. The eigenvalue would be multiplied by its corresponding identity matrix so that it could be subtracted from its matrix. And since the eigenvalue is non-zero, then this expression must be 0 or equal to a 0 matrix. A 0 matrix has a determinant of 0, so this equation is true. Note that this equation is now in scalar numbers and not vectors. And so this determinant expression is equal to the characteristic polynomial of this matrix A and is equal to 0. So the eigenvalues are the roots of this polynomial. So we are now going to write a computer program that finds all of the roots of this polynomial. And so we have to search for the first root. We'll find it using Newton's method, but Newton's method isn't guaranteed to converge. We'll use two tricks to make it more certainly converge. Firstly, we'll use a softening value to stop overshoots from steering us away from the root. It can be any number between 0 and 1, but 0.9 is a good value to use. A second trick is to use all of the complex number plane to find it. Using a complex number as an initial value helps us to use all of this number plane, and it is necessary because the root is sometimes complex. Using all of the complex plane helps Newton's method to converge a lot. So these are the two polynomials that we'll need. We need the derivative of the characteristic polynomial. And so this is the form of Newton's method that we'll use. And so using this iterative equation gives us all these values of lambda, which converge very closely to a real number. Notice that the imaginary part is extremely small. And these are the corresponding values of the polynomial for these values of lambda, and they converge to 0. And so, to find the next root, we have to divide the characteristic polynomial by x minus the first root, which looks like this. So we'll have to do some polynomial division. So to observe polynomial division, we'll demonstrate it on another polynomial and root, so it is easier to see. So I guess if you're interested in linear algebra, you'd be very familiar with polynomial division. So here is what it looks like quickly, to get a bit more familiar with it again. Since it is a root, the first polynomial divides the other polynomial with 0 remainder. And so this is what we've found as an answer. And we'd have to look for the next root by applying Newton's method to this polynomial. And now it's time to define a polynomial type. It consists of two attributes: its degree, or what is the value of its highest power, and an array of all its coefficients. And so here is an example of a polynomial that we want to store in the computer. And so this is how it is stored. And this is an example of how to get the coefficient of x to the power of 1. So now it's time to write a computer function to find the quotient of these two polynomials. So the degree of q is 1 less than the degree of p. And so we take the leading coefficient of p before we enter the main loop. It is usually equal to 1 or minus 1, depending on the degree of p. So then we enter the main loop. We step backwards through the polynomial, because this is the order in which it is done in long polynomial division. This loop must span every coefficient in Q. And so this little bit of algebra simulates division by x minus lambda. The remainder of this division should be 0. And now to write a function that evaluates a polynomial for a particular value of x, like for example x is equal to 1 or x is equal to 2. We first set a variable equal to 1, which will then equal x, and then x squared, and x cubed, and so on. And we'll set y to equal the polynomial evaluated for x. It is a cumulative total, so it is initially equal to 0. So we start the main loop to span all of the coefficients of p, and we'll evaluate each term in the polynomial and add it to y, and y will be the answer as a scalar number. So now to create the polynomial derivative function, which is very simple for polynomials. The degree of the derivative is always 1 less than the degree of the original polynomial. And so we loop through all of the coefficients of p except for the constant. So we skip I is equal to 0. And then we use this simple equation to find the derivative of each term of the polynomial. So when we get to the last root, it is in the form x minus a. So the root would obviously be equal to a, because it is a line, which can be solved very easily and obviously. Or you may choose to solve both the last and second last roots using the quadratic equation. So I hope you can put all of this together to make a computer program to find all of the eigenvalues of a matrix. The next step is to find all of the eigenvectors that correspond to each eigenvalue.